Okay, in this problem, we are dealing with Newton's laws of motion, his first, second, and third law, primarily his second and third law. And we're not going to need too much calculations at first, so we're just going to have the do everything symbolically and then calculate at the end. But let's talk about what's going on. So as shown, we have a small block of 2.5 times 10 to the negative 2 kilograms, or 25 grams, which rests on a ramp of mass 8.8, or sorry, 0.88, or 880 grams. And the ramp has an incline of 62 degrees. That's the incline that's shown here, above the horizontal. The surface of the ramp is frictionless, so this problem does not involve any friction. And the ground is also frictionless. As I said, no friction. The ramp is not attached to the ground. It's free to move. So the system is released from rest. Okay. So what's going to happen, to kind of give us an idea, is we can say intuitively block M will slide down and to the right, which we will call the positive direction, and we'll call up the positive direction as well. All right, so I'll go over here and define our coordinate axis. So we're going to have positive x over here, and then positive y in this direction. Okay. And so that's block M1. And ramp, okay, M2 will slide to the left. Okay. Okay, that's certainly what's going to happen. Now, they're different masses, so even without the angle of the ramp, which will change the problem further, we would not expect mass 1 and mass 2 to have equal accelerations. Because if they were to, say, push on each other with equal force, then M1 would accelerate more because of its smaller mass, and M2 would accelerate less. And that's just based on Newton's second law, which says F equals ma. Okay? So we're going to use, okay, so our key formulas here to set up this problem are going to be the Newton's first and second laws, which just says that F equals ma and FAB equals the negative of FBA, both as vectors. Okay, and both these laws I wrote as vector equations. Okay, so let's go ahead and draw all of the force vectors that act on the system, and then move on from there to set up our sum of forces. Okay, so I'm definitely going to refer to this one as step 1. Okay, so here, step 1. Okay, and what is step 1? Draw all the forces acting on both free bodies. So draw all forces on free bodies. Okay. All right. Okay, so what that looks like is we will show that we have a number of forces acting on both objects. Let's start by thinking about object 2, the ramp. Well, there would be a normal force acting on the ramp, pointing up from the ground. Okay, so that would be Fn. The ramp also experiences a gravitational force, and the location of that gravitational force is not very crucial yet, not until later chapters in this course. Okay, so that's Fg. Okay, then we have Fn as drawn. Okay, we also have a the acceleration of the ramp, but we'll worry about that later. But then the ramp is also experiencing a gravitational force exerted by m1. Okay, so then I'll draw that like so. So this right here is Fg1. Okay, so Fg1, and this one is Fg2. Okay, and those are all the forces acting on M2. 3 forces: normal force and 2 gravitational forces. Because again, there's no friction, so no other forces. All right. Meanwhile, on M2, which I'll use a different color for, on M1, I'll use a different color for, and the forces acting on M1, well, there's gravity. Okay. All right. So that right there is Fg1, the same force that acts on mass 2 is acted on by the Earth on mass 1, okay? And then mass 1 also experiences a normal force. But interestingly, the normal force, by definition, normal forces are orthogonal to the surface, right? Which is why we had the normal force exerted by the table or floor on the ramp at 90 degrees, right? So that means that the normal force exerted on mass 1 must also be 90 degrees, which is going to make it not point straight up. Okay, so it's going to look like this. All right, and that's going to be Fn2. All right, and we'll call the first one Fn1. All right, so we've denoted all 5 of the forces that act in the system, with 2 forces acting on mass 1 and 3 forces acting on mass 2. I'll go ahead and draw the accelerations as well, what we're going to be solving for in parts A and B, because we're going to solve for both the magnitudes and directions. Okay, so if we draw acceleration 1, and I'll draw these nice and large so we can clearly show the components, and we'll have to show some components of the normal force too as well. But those are really the only components we're going to worry about. And it's good to point that out and think about that. Since we did choose an axis system that was not tilted, we had to think about the justification for that. But the reason that we chose an untilted coordinate system is when we look at all the forces that are acting, the 3 forces that act on M2 are all in the y direction, either negative or positive, and one of the forces that acts on M1 is also point straight down. So the only time we have to worry about components would be F2. Had we chosen a tilted coordinate axis, right, that was parallel to the ramp, well, then we would have eliminated the need to have components on F2, but we would have introduced the need to have a lot of other components. Okay, so this would be A1 here. All right, and then we're going to have A2 going straight back this way. Okay, like so. All right. So that will be A2. All right, so let's go ahead and write our sum of forces, which we will call step 2. All right, so step 2, write the sum of forces. Forces on both blocks in both axes. And I say both blocks, I mean the block and the ramp, or we can maybe think of one as a ramp-shaped block. So write the sum of forces on both blocks in both directions, x and y. Okay, so let's write our sum of forces in x for 1, sum of forces in y for 1, and the same thing for object 2. Okay, so sum of forces x1, sum of forces x2. All right, here, let me change pin style. Let me write this. Sum of forces x1, sum of forces x2, y1, sum of forces x2, and sum of forces y2. Okay? So what are each of those going to look like? All right, well, for the first one, we're going to have okay, so an x. All right, for object 1, well, we're going to have a component of the normal force, so we'll call that Fnx, okay, and then that's going to equal a component of the acceleration force, so that would be m1a1x, okay, and now I will go ahead and draw those components on our trusty acceleration vector, and that's for object 1 at least, okay. We don't have to worry about components for the acceleration vector on object 2 on the ramp because it goes straight to the left. Okay? So this would, here we'd have a x1, and here this is a y1. And the reason I wanted to do that now is because I wanted to highlight the fact that a x1 does point in the positive direction, so that we don't have to worry about it having a negative. But in y, well, it's a different story. So then we have, if we look at the forces acting in the y direction on object 1, we'd have F and y pointing up, okay, so positive. And then we're going to have the gravitational force, which I'll write as m1g. So all I've done is just write F sub g1 as m1g, because that's what it is. Okay? And then that's going to equal negative m1 a1y. Okay? So far, so good. Let's do the same thing for the ramp for object 2. All right. Well, the ramp in the x direction, well, the only thing we have is the negative of the normal force acting on it, okay? Because, let's write that in, F and x. Okay, now this is a key point to pause and think about what's going on here. So what I wrote, and actually I have to correct myself. So okay, so I wrote that the three gravitational forces acting on the ramp on mass 2 were going to be the force of gravity acting on it, right? That's a non-contact force, a force at a distance. The normal force exerted by the table, okay, or ground on the ramp. And then I said, oh, well, also mass 1 is pushing on it, so it has to push back. But I show that vector pointing straight down. And that I have to correct because that vector is created by the normal force. It is created as a force pair. So what happens is that if we go back through our steps and think about Newton's second law, we've got gravity acting on m1. Well, m1 then also acts back on the Earth, pulling with an equal force. Of course, the Earth is so massive it causes absolutely negligible acceleration. Meanwhile, mass 1 is in contact with mass 2. That mass 1 wants to accelerate due to the fact that it has inertia and is being acted on by a force at a distance, gravity, but it can't. It pushes into the solid surface that will not give way. Thus, the surface pushes back, and m1 pushes with the normal force, and the surface must push back with a force that's equal in magnitude and opposite in direction. So in fact, what we have here is Fn2 just acting on m2. Okay, so it'd be Fn2. All right, so before I wrote it as Fg2, or Fg, and I see I mixed up some of my subscripts here. All right, so because this everything for 1, right, is like so, and then, okay, so this is 1, and then this one is 1 as well. Okay. Okay. And so, and that's also, yeah, it was when I was labeling all my normal forces at the end that I switched some of them up. So this one should be a 2 as well, because the ramp is 2. I momentarily thought it was 1 because it was larger, but it's object 2 in this system. So this is the correct force. It does not point straight down and is not equal to the gravitational force. Okay, and that's a key part of this problem. It is the most subtle part of this problem. It's part that I rushed through when I was first drawing my sum of forces, and then it was called attention to me when I was thinking about actually writing them out. Okay, so let's move on, and we can refer back to that if we need to. Well, that's going to equal negative m2 a2. Okay, and then in y, what are the forces acting on the ramp? Well, we've got Fn. Okay, and this is, let me label that correctly over here, not just F2, Fn2, and so that would be Fn2. Okay, and these of course are y over here, and then we've got the gravitational force minus m2g, and then we also have a component of the gravitational force. We're going to have minus Fny. Okay, and yep, and we'll see how that works out, and you'll see that it works out quite nicely, and that would be Fn1y, right? Because that's just the component of this force here, because that force does have two components, 1 and 2. Okay, or x and y. All right, so we got a 1 there and a 1 there as well. Okay, so oh no, that one is Fn2. This is Fn1, but the x component, right? So we have a whole series of subscripts here. N for normal force, 1 for because it's coming from object 1, and x because it's the x component. And then we've got its other component over here, the normal force coming from object 1, acting on object 2, but the y component, the vertical component. Okay, excellent. Okay, so now we can go ahead and start solving the system. All right, so what does it look like? All right, so for part A, we're asked to solve for the magnitude and direction of the acceleration of the ramp, okay? So we're trying to solve for A2. So in part A, I want to solve for A2. All right. So how do we go about doing that? Well, we can then say that A2, right, using just the sum of forces in X, is going to be Fn1 X component divided by M2. Okay? Okay, and this is going to lead to a series of algebra substitutions and simplifications, which I'll kind of jump through, but still show you the key steps. So the first thing in solving A2, we want to look at this unknown value, the normal force acting on object 1, and we can look at the sum of forces on object 1 in X to see that the normal force in the X direction is just equal to mass 1 times the acceleration in X. And that's what I've wrote here. And then I have expanded that out to show that the X component is cosine of theta. Okay, and so simply the connection I made here is that this value right here is theta, okay, which makes sense from a geometric point of view. And here I can say that if I expand out the X component of the normal force acting on block 1, then I get Fn sine theta. Why do I get Fn sine theta and not Fn cosine theta? Well, if we go back and look at our sum of forces, and we look at the normal force, which I'll move the label out of the way over here. So here is our Fn1. Okay, so we can see it has two components, a vertical and horizontal component. Okay, so these are the two components of Fn1, so Fn1y, and this one here is Fn1x. All right, so they're the two components. And what's the angle, right? Well, what's going to happen is Fny is going to become all of Fnx as theta approaches 0. So, okay, well, in that case, this right here has to be theta, right? Because then we're going to have that at sine of 0, we have that all of Fn1 is Fny. And sure enough, sine of 0 is going to be it's going to give us that value. Okay, well, let's think for a second on that. Yeah, so what I was saying is that the Fny component has to be the cosine component as it is with regards to the angle, because we need cosine of 0 to equal 1, which is then going to give us the correct notion. In other words, that as this angle here shrinks and goes away, this angle is also going to approach 0. Right? And that's one way to always kind of think about the geometry without getting into complicated rules. Okay, so then now that we have that notion, we can go back and think about what we were doing here with our forces and the algebra to solve for the acceleration on block 2. And so I had made this step here where I was looking at the X component of the normal force acting on block 2, and I'm saying that it's Fn sine theta. And now we can see that up here, that indeed it's the opposite of the angle defined as theta, and so that's why it's sine. Okay. Okay. But you can see we currently have an equation here, this equation, where we have two unknowns, Fn and A1, and we're trying to solve for A2, which isn't there yet, although we'll get there. And so what I want to do is to eliminate F1, okay, or eliminate Fn. Okay, and to do that, I'm going to look up here, not at the sum of forces on block 1 in the X direction, but instead look in the Y direction. Okay, and so we have from there, we have Fn1y minus m1g is going to equal negative m1 a1 sub y. Okay. So then we can expand that out a bit, and what that will look like is Fn cosine theta. We already talked about why cosine of theta is the y component of the normal force. Okay, and then just minus m1g. Excellent. And then that's going to equal negative m1 a1 sine theta. Okay, and now let's solve for Fn, so we can substitute it back into this to the equation above, which I will underline in green. All right, so we can substitute back into our green equation. This one right here. Okay, so we're going to solve for Fn. Fn1, of course. All right, and what that's going to look like is that's going to give us m1 a1 and then sine over cosine, which is cotangent of theta. Okay, and that's simply from this expression right here. Okay, or let's see, well, rather that's from this expression up here, Fn1. That's just taking cosine over sine. All right, and that gives us our cotangent. However, we need then to plug that into the equation here. Okay, I'm going to plug this in right there. All right, so we're going to take that Fn, which we got from the green equation, and we're going to plug it in to our purple equation here. Okay, so then what does that look like when we do make that substitution? Okay, well, that's going to become m1 a1 cotangent of theta, all right, times cosine of theta, and then minus m1g. Okay, because again, this is the purple equation, which was got from the sum of forces in y on block 1. Okay, and then that's going to equal negative m1 a1 sine theta. So you can see a big part of what I'm doing here is taking all the components, which I wrote entirely in terms of just all their subscripts, and making sure to include all the angles in the appropriate places, so that we can algebraically work with the trigonometric functions. Okay, so what I have done inadvertently here is actually ended up solving for really a1. I think I'm going to be a better place to solve for a1 first. So we'll get that value, we'll kind of collect it, and then once it's asked for in part B, we'll refer back to it and plug in the actual numbers to solve for it numerically. But in the meantime, we'll use it as an algebraic tool to get all the way back around to a2. And that's okay sometimes. We do a path that isn't the most direct, but as long as we're asked for one part or the other, we will get there. Okay. So I'm going to factor out the a1 and move some terms around. So this expression is then going to become a1 times m1 cotangent of theta cosine of theta plus m1 sine theta equals m1g. Okay. And so then we have that a1 equals m1g, and then divided by m1 cotangent theta cosine theta plus m1 sine theta. All right. So, and again, I'm keeping everything in terms of, just algebraically, not symbolically, I should say. And so we're going to be a place where we can definitely solve. We can solve for the normal force if we wanted to. We can simplify the whole expression, and then we can eventually get back to a place where we can solve for a2, because one of the key ideas that we have is if we can find the normal force in general, then we can go back here, the part that I've underlined, and then just insert the appropriate component, in this case the x component of the normal force, which if we recall is sine of theta, and then we can just multiply whatever we got for solving for the normal force to get that. Because I should point out, right, just to say it again, this is it. This is a1 in terms of known quantities. We know the angle, which comes up a few times, and obviously we could simplify this, and we certainly know m1 and g. So we're really at a place where we actually have solved completely for a1, and we could plug in our numbers at this point. Okay, so, but before we do that, let's solve for the normal force so we can actually get back to solving for a2. Okay, so I can just continue a little bit more of the algebra, but I wanted to show you what step we're at right here. So I went ahead and just solved for the normal force by itself in terms of our new found value. Okay, so we just solved for acceleration 1, and I'm going to plug that in to the normal force, which is m1 a1 cotangent theta, which we know from above. And then I went ahead and simplified that expression, canceling out one of the m1s. And now I'm going to use that information to relate it back to m2, because we know that m2a2 from the sum of forces on the ramp in x is equal to the x component of the very same normal force we've been working with. Okay, so then that would simply be this whole expression here, which is the normal force. So m1g cotangent theta, and then all divided by cotangent theta cosine theta plus sine theta times sine theta, because we're looking for the x component of the normal force. Okay, so we can do that, move that over here. Okay, and so then we can go ahead and simplify that expression to solve for a2. Okay, so I have continued to work with that expression and got it to a point where I can show you, hopefully. Let's see. Let me make this so it's visible. Okay. Okay. So what we've done here is solve for a2. Okay. So solving for a2 here. And I've done that by multiplying both the top and the bottom by sine theta. Right, so I had a sine theta here, which just came from the component, but I went ahead and distributed that sine theta in, which gave me my sine squared, and then I did multiply the top and the bottom by sine theta, basically getting a common denominator to simplify things. And I'll let you work out that algebra and see how that step works, but we went from here to here. All right, and so now we see that the denominator of the expression is just going to become 1 by the trigonometric identity. It says cosine squared theta plus sine squared theta equals 1. So we get a very nice result that the acceleration 2 is just going to be m1 over m2 times g cosine theta sine theta. Okay, and so now we're able to find both answers to part A and B. So I'm going to go ahead and identify those and put boxes around them. All right, because we ended up solving for them somewhat simultaneously. But we can refer back to the problem and make sure we've answered the question. And the result for A2 makes a lot of sense if you think about the fact that it's cosine theta times sine theta, because if the ramp was entirely flat, then it wouldn't move. And if the ramp was entirely vertical, right, if it just went straight up, well, then there would be no normal force. The block would just slide straight down, and it wouldn't cause essentially what would be a wall to move. Okay? So in both cases of 90 degrees and 0 degrees, we should get a 0, which indeed we would. Okay? So let's plug in our values. Okay? So in the problem, we've got that theta is 62 degrees. All right, so let's go ahead and plug in. I'll plug in for A2 first, since technically that was asked for first. All right, so let's turn on our calculator over here. All right, so we've got, it's m1 over m2. So m1 is the 0.025, okay? And that's going to be divided by 0.88. Okay, so that's the first expression. Let's put that in parentheses. So we'll go ahead and insert parenthesis here. All right. And then we're going to be multiplying that by the rest of the expression, which is 9.8. So 9.8. And then again by, and I'll scroll down so you can see what I'm doing here. We're going to multiply that by the cosine and sine. Okay? And the angle is the 62 degrees. Okay? So it doesn't matter which one we do first. Let's go ahead and do cosine. And so cosine of 62 degrees. Okay, and then close the parenthesis on that, and then multiply by sine of 62 degrees as well. All right, sine of 62. All right, let's get that answer. All right, so we get an acceleration of 0.115. All right, so that would be 0.115 meters per second squared. Okay. And indeed, what is the magnitude and direction of the acceleration of the ramp? Yep, so that is part A. Okay. But because of the way we got there, we already have the answer to part B, I believe, which says what is the magnitude direction of the acceleration of the small block. Okay, so let's go ahead and solve for that. Okay, and actually let's, and here we're not going to get the direction. So here I can say, and I'll go ahead and write the direction, first of all, for the ramp, which is the reason I think it was asked for first, because it's the one that's it's a more straightforward direction. So here we have that this is to the left. Okay. But for part B, we're going to solve for the magnitude up here. All right, I'm going to put it in right here. But that will not answer the direction question, which we'll follow up and answer in a minute. Okay, so the magnitude we're going to get, so we're going to have m1. So we'll start with 0.25. All right, and let's put this actually in parentheses. So it's going to be our numerator, 0.025. And then we're going to be multiplying that by 9.8 by gravitational acceleration. All right. All right, and we'll close that. And then let's get our denominator expression, which is quite a bit bigger. We have, okay, so then we've got m1 again. So actually, we should have canceled out our m's because they're not going to be relevant for the problem because they all cancel. All right. There we go. All right, and I'll show that here as well. All right. So, okay. Okay, so then let's get to our angles. So we have cotangent, which is just 1 divided by tangent. All right, so 1 divided by tangent. Okay, well, we actually don't want second. We just want 1 divided by tangent of our value here, which was the 62 degrees. Okay, so 62. All right, and then that's multiplied by cosine. So then times cosine of 62. And then we're going to be adding sine, plus sine of 62. Okay, close out everything in the denominator. And we get 8.65. All right. And that would make sense. It's much less massive, and so it should be accelerating quite a bit more. Okay, and so that's the magnitude of the acceleration on block 1. But we need its direction still. Okay, so again, we were asked in part B, what is the magnitude direction of the acceleration of the small block? So here, I'll put a block around this and say magnitude for part B. Okay, but in order to find the direction, we just need to find the x and y components of the acceleration. Okay. Well, we already know the angle, so we can find that information pretty straightforward. All right. So, or rather, we know that it's following the angle of the ramp, right? So, I can see here that if we look at the acceleration, it has to follow the ramp. So it's no mystery in the sense of like a projectile motion. When an object crashes into a wall, we don't know how fast it's moving. It can crash it at an angle that's completely created by the kinematics before it crashes. But here, we know that m1 is going to slide down the ramp. It's not going to lift off the ramp or bore down into it. So we know that it's going to be going down at an angle of 62 degrees. So we can say that here, down and to the right. So down and to the right at 62 degrees below horizontal. Okay, so that answers part B and part C. So then we only have part C to answer, which will give us a distance and ask and say if that lower corner is a certain amount above the ground, how far will the ramp have traveled by the time the corner touches the ground? Okay, so we're going to use some kinematics here and find exactly how far things move just by taking all the accelerations that we solved and plugging them into kinematic equations. And I will not solve that solution now, but I will leave that up to you. And thank you.